Modifiers. Think of modifiers like some extra tools in your toolbox that enable you to fine adjust your tolerances to be more precise. This has two main advantages. First, they enable you to control only what is most relevant to the function, and second, they prevent measurement conflictions. Let me explain what I mean with this story. If we have this innocent looking feature here, a simple hole, you specify the diameter to be 10 plus minus 0.1. You get the measurement report and the part has passed, but during the assembly you have problems. So you send the part to another measurement lab and you get a different result. You send it to another one and you get a third result. How can it be that one feature has three different measurement results? You make a meeting with all the measurement technicians and everyone repeats the measurement, only to find that technician 1 measured the distance between two opposite points, repeated the measurement 10 times and gave you the average as a result. Technician 2 said the function of the hole is that a shaft will be assembled inside it. So what matters for the function is that a gauge with a diameter of 9.89 will pass through it and a gauge with a 10.11 will not pass. So he used a gauge to measure the diameter. The third technician measured just as technician 1 but in a different cross-section. This confusion leads to endless discussions and a lot of lost money. This is where modifiers come to play, and this is only one of the advantages of modifiers. Let's look at them in more details. There are hundreds of modifiers and modifiers combinations, and there is no point of just listing all of them here. But let's look at the main groups of modifiers, and the most famous ones in each group. Even if you meet a modifier later that you haven't met before, you will know from which group it is and what is it modifying and how to look it up. Modifiers can be divided in specification modifiers, complementary specification modifiers, tolerance zone modifiers, material condition modifiers, and modifiers of the tolerated element. Specification modifiers. Specification modifiers are those that will solve the problem with the measurement technicians. These modifiers has this oblong shape and consist of two letters. The first indicates the type of the size dimension, and the second indicates the way or the method of evaluation. The first letter can be an L, which stands for local, a G, which stands for global, a C, which stands for calculated, or an S, which stands for statistical. As an example, let's look at L and G. L having by definition a non-unique result of evaluation along or around a feature of size. This means there is a different result of the measurement if you change the cross-section or rotate the part. Just if you rotate the part a little bit or you change the cross-section, you get every time a different result, and this is called local dimension. So L stands for local. G, on the other hand, is a global dimension. It means having by definition a unique value along and around a toleranced feature of size. So the result takes into consideration all the cross-sections and all the rotary orientations of the part. And this result is a unique value. Regardless of how often you repeat the measurement, you always get the same result. How is this achieved? Let's have a look at the second letter. The second letter can be one of 15 letters. Each indicate how the measurement is evaluated. Let's look at P and X. P stands for points. Means the result of the measurement is the distance between two opposite points. It's the most common method of evaluation. This is the direct result that you get from a micrometer, for example, or a vernier caliper. If you measure the distance between these 2 points here, if you just rotate the part a little bit and you measure the distance here, you get a different result. And so a P measurement can only be local, so it can only be combined with an L. So you can see LP as a modifier. And also if you change the cross-section in which you measure, you will get a different result. N stands for minimal. It means the result of the measurement is the size of the smallest possible enveloping geometrical element. The result of the measurement here is the size of this circle. An example for a GN measurement is the measurement of a shaft diameter using a ring gauge. It's completely independent of the cross-section and the rotary orientation of a gauge. If you rotate the gauge, you still get the same result. X stands for maximal. It means that the result of the measurement is the size of the biggest possible enveloped geometrical element. So for the same hole diameter, the result of the measurement with an X is the size of this circle. So an example for a GX measurement is evaluating a hole diameter using a pin gauge. There are, of course, tens of other possible combinations that you can generate. The meanings of the different letters can be found in the ISO 14405 and ISO 1101.